Let's look at another related rates example. So this one is about throwing or dropping a stone into a calm body of water. It creates these ripples that in the form of concentric circles, and they kind of move out from the point of impact of the stone into the water. We're going to look at the outermost circle, that first one that comes out. Clearly this is a circle in motion. So there's some stuff changing there, and we're going to need to use, if we want to find and talk about the rate of change, we're going to need to use a related rates equation. And again, we're going to look at what rate are these quantities changing at a moment in time. We are going to freeze it at some point and say, at this moment in time, this is how fast stuff is changing. That's not an official math term. Okay, so identify all the variables involved in the problem. So we've got, let's see, area of a disturbed water. Mr. Hill says that's his favorite type of water to drink. And we'll use a capital A for that. Then we've got the radius of the disturbed water. And we'll use an R. Identify which, if any, of the variables in the problem that remain constant. So as that circle is increasing, is the area changing? It is. The area of the circle is getting larger. So that is not a constant. And the radius is also changing as the circle is increasing. The radius, the length of that from the center of the circle out to the edge, is also increasing. So we're going to say neither area nor radius are constant. Now we want to look for rates in the problem. What rate are we looking for? What rate are we given? So if our variables are A and R, that means most likely we got to know or want to find dA dt and then a dr dt. Those are typically the rates that are going to show up. So let's see. They have a foot per second here, so that's a rate. Is that the rate of change of the area or the rate of change of the radius? Well, we know it's a rate because of the per second part. When we talk about a foot per second, it wouldn't be area because area would be in feet squared. Radius is measured in feet. It's a length, it's a distance. So that's 1 foot per second. The rate of change of the area is what they're asking. At what rate is the total area of the disturbed water changing? So that's what we want to find. So we want to write an equation in this one. The equation we're talking about here is we're talking about the area of a circle. So when I write the equation, I have to use A and R. I cannot put in numbers for R. Even though it says in the problem when the radius is 4 feet, I don't plug in a 4 for R here because R is changing. We have to wait till after we find our related rates equation, which is the derivative. So the derivative of A is 1 times dA dt by chain rule. Remember, pi is just a constant here, so the derivative of pi r squared is going to be 2 pi r times the derivative of r with respect to time, or dr over dt, because of chain rule. Now we're going to plug in the values. We can now freeze this thing and look at the moment in time that we want to investigate. So dA dt is what we're looking for, and the moment in time is when the radius is 4. So I can plug that in for 4 times the rate of change of the radius, which they told us was 1 foot per second. We simplify. And again, you could pause and get ahead of me if you like. We get 8 pi feet squared per second. That's the rate of change of the area of the circle.